have Alice, and we have Bob, and we want, or Alice wants to talk to Bob, but they don't want to be, eavesdropped on by Eve. These are the technical terms, by the way. So, what should Alice do? She can't just talk to Bob and just say, hey, what's up, Bob? No, she doesn't want Eve to know that she's asking Bob, what's up? So, what she could do is she could encrypt her message and say, and then Eve would be like, what the heck? And this is exactly the ciphertext, as we call it. So she wants to send her message M, so she kind of encrypts it, and then sends it to Bob, and Bob can somehow decrypt it. And we talked about these three things, that the message, this is the plain text. We have C, this is the ciphertext. And then we have a key, K, which is used in order to encrypt this message. And I'll get into how that functions, but this is the basic setup. And Eve doesn't have to necessarily be a eavesdropper, but can be active. I'll get to that. Before we get that done, I'd just like to talk a little bit about bits, because I'm not sure everyone knows what they are. So bits are basically zeros and ones. These are the things that computers they work with, and we have a string of bits, or a bit string. Could be 0, 1, 1, 1, 0, and then 1. And if this is n, then there are n of these. And we have something called the bitwise exclusive OR, which we also call, we write it like this, but we also call it XOR. I'm just going to call it that. And basically the way that it works is that we have four possibilities. We have 0 XOR 0 is equal to 0, 0 XOR 1 is equal to 1, 1 XOR 0 is equal to 1, and 1 XOR 1 is equal to 0. So for those of you who've had some algebra, so on, you might notice that this is simply modulo 2, addition 1 modulo 2. So that's what we basically use, and if we have two bit strings and we want to XOR them, then we do it bitwise, and then get something out of it. Okay, so, let's look at some classic cryptography. This is the stuff that they used to do in order to encrypt their messages. Particularly Caesar had this one that we call the Caesar shift. And basically, it works like this. You take the entire alphabet and you shift it by your key. In this case, I'm taking my key to be 3. And so I'm shifting the entire alphabet. So A gets sent to B, B gets sent to E, and so on and so forth. And it wraps around, so Z gets sent to C. Okay? So basically, if we want to encrypt the message, begin the attack now, B gets sent to E, E gets sent to H, and so on and so forth, and we have this message. This we can send off, and then decryption. Basically, you shift your entire alphabet backwards by 3. So now B will be sent to A, E will get sent to B, C will get sent to Z, and so on and so forth. And we basically have the original message. E gets sent to B, and so on. Okay, what's the downside? Well, this can be brute force. We can simply check all the keys. There are only 26 of them, or 27 of them, in English, and in Latin it wasn't a problem either. But back then, very few people actually knew how to read and write. So then it was kind of secure because it was secured through obscurity. Nowadays, we don't have that luxury. Pretty much everyone knows how to read and write, and yeah, you can brute force this, as we say, in polynomial time. Polynomial time basically means that we can write out the polynomial, and that's the amount of steps for a message of length n. Then it has p of n many steps in the algorithm, which can be used to decrypt it, or break it. There are different variations of this, something called a substitution ciphers, where instead of using the alphabet, we kind of write the message And then underneath we kind of write a word and just repeat it, and then we shift in some ways. But the matter of fact is, it's still, we use the same word, so we can break it in polynomial time just by brute force. All of the classical ones can be broken by brute force. So then the question came up, what can we do to have something be secure, right? Well, is it enough to say that it should be impossible to recover the key? Is it enough to say it's impossible to recover the entire plain text? Or is it enough just to say, well, as long as they don't get, if it's only a little bit of it, that's fine. That we'll still have some kind of security because they don't know everything we're saying. But this is a problem if, it's a bit which kind of says whether it's $1,000 or $10,000 you're sending to the bank. That's kind of information that you'd not like people to know. And what about additional information? For example, you have the Enigma machine that pretty much everyone has heard of, that the Nazis used during World War II. It was an actual machine in order to encrypt and decrypt. So basically, if you just got your hands on that thing, you could basically decrypt the entire thing. Or figure out how the encryption scheme worked. That's pretty much what they did. Yeah, so then we also think, well, what are the different scenarios that we might have? Like, what kind of adversaries are we against? Is it one that only sees our ciphertext? Is it one that knows what Alice might want to send? Like M0 and M1, there are only two choices, so it gets a C out and then it has to determine which one it is. Or is it chosen plain text in a way that the adversary can kind of tell A to encrypt M prime, and then it checks that that comes out. Let me give you a practical example. Also during World War II, the Americans had kind of broken the entire encryption scheme of the Japanese, except they didn't know how they'd kind of coded base names and names in general. So basically, they got this message saying that, oh, we're going to attack A very soon. And they were like, what the heck is A? We don't know what A is. But they kind of traced it down to 3 different bases. And they were like, okay, it's got to be one of these. So let's say that Midway has water problems, this other one has sanitation problems, and the third one is missing bug repellent or something. Okay, and then they put those rumors out there, and then soon they got a message that they decrypted saying A has water problems. So they're like, Midway, right? Okay. So these are actual scenarios that we could have, You might not directly be able to encrypt something, but you might be able to get Alice to encrypt something for you by tricking her. There's also chosen ciphertext where you can actually influence her to decrypt a message and also show you what the message was and stuff. But I don't have a rational argument for that. Well, I haven't thought about it. But anyways, so this is the kernel of it. We need to actually say what is an encryption scheme and when is it something called perfectly secret. This is like the best way we can get something secret. No one's ever going to break it, except for God, but he already knows what the message is. Everyone else can just go F themselves, because there's no way they're going to break this. And I'll get into what it means to not be able to break this. But let's see, so we define an encryption scheme to be this pi, using these 3 algorithms, the generated, encryption, and decryption. And we start with the message space M, and this is the message space of all possible messages. So think every combination of words in the English dictionary. And we kind of say it has to be strictly greater than 1, because if there's only one message, there's not really anything to work on. You can kind of guess the message. Okay, so then we have a key generation algorithm, gen, and it has to be a probabilistic algorithm. And we say probabilistic because if it's deterministic, I can always figure out what the key is going to be. The key needs to be random, so to speak. It doesn't need to be uniformly random, but we usually suppose that. It's easier to work with, and it does some better things.
What does uniformal random mean?
That means that each key is distributed with the same probability. So if we have the bit strings of length n, then it's 2 to the power of n. Each message has the same probability. then we take the encryption algorithm. It takes k, and we affix it as an index because it needs to be fixed for the entirety duration of the use of this encryption scheme to talk between two people. And then encrypted message M, and we call this our ciphertext C. Then we also have the decryption algorithm, again using the exact same key, but on some random ciphertext M. And there's a point in the fact that these are definitely either C or M, and this is definitely in the message space or in the ciphertext space, because we have something that we call perfect correctness. And perfect correctness simply states that we have a kind of bijective correspondence here. So that if I decrypt using the key K, some kind of encryption also encrypted using the key K, then this is going to give me a message M every time. Yeah? Later we have that the ciphertext space could be larger, so then we don't necessarily have the same thing, but I'll get into that when we get to it. And yeah, so with probability 1, basically this always happens. Okay, so now let's get to it. What does it actually mean to be secret? We've only defined an encryption scheme. Now we're defining what perfectly secret is. Okay, and without getting too much into what it says, but we're saying for every message M and every ciphertext C, this is a technicality, we have that the probability distribution of us getting a message M when we have a message or a ciphertext C is going to be equal to the probability that the message is M. Basically, that the cipher text and the message text or plain text are going to be independent of each other. And you can think of it in the way that if the probability that the message M is kind of a die, so this being 1, well, this doesn't impact if I have another die that I just roll at the same time, and I get 2 here, that this is necessarily connected. No, they're 2 different die. Why would they be connected? Of course, there's this whole encryption thing, so there is some connection, but it should seem like there isn't. That's what the secrecy says, the perfect secrecy. So we have this experiment, because we don't, right now I've just given you this definition, but how do we prove this? How do we actually know when something satisfies this? Well, we have another definition, lots of those in this, this subject, and basically we have an experiment. We love running experiments, and these experiments are kind of thought experiments, because we say, we kind of idealize. We say, in the best of conditions, for the adversary, what's the chance that he wins, that he can guess which message he's sending? And what we do is, we simply let, I'm going to write it up here on the bottom, we let the adversary choose 2 messages. How? No one knows, except for him. They have to be the same length, because otherwise it's going to be very easy to distinguish between ciphertexts. And then he basically sends them to Alice, or us. We're playing Alice's part in this case, because we kind of want to show that he can't break it. So Alice, what she does is, she gets a random bit B, which we also sometimes note like this, but it's a random element of 0 and 1. So each has probability 1/2, and then she simply chooses to encrypt using her secret key, which he doesn't know about, or the adversary doesn't know about, MB. Yeah? So each of these has 50%. Can someone close the window? Adrian, could you roll down the blinds, please? Thank you. So each of these has 50% chance of being encrypted. Perfectly 50, right? So then, this is the C the adversary gets, and he basically has to say, he has, yeah, so to the adversary again, and he has to output some bit B, and if B prime is equal to B, then he wins. If B prime is not equal to B, then he loses. Okay. And exactly when the possibility of him getting this right versus the possibility of him getting this wrong is exactly half, then we have perfectly indistinguishable. This basically means that he's not able to distinguish between the encryption of M0 and the encryption of M1, which is what we want. Because we want the ciphertext, the encryptions, we want those to be secret. We want him not to be able to say which one we've sent. This is idealized, but this is in essence what every single form of security that we might cook up actually boils down to. And yeah, so we have a lemma that gives us that an encryption scheme is perfectly secret if and only if it satisfies this probability distribution. We have an example, which is the one-time pad, which uses, basically you have a message in bit strings of length n, and you XOR it with a bit string, or random bit string, which is the key of length n or greater, and then the product of the two, or the sum of the two, the XOR of the two, is going to be perfectly distributed, right? Because the first bit string might have not been random, but the second one is. So you're basically just XORing with something random, you get something random. But why is it called one-time pad? Because XOR is really stupid, and if we use the same key twice, we can just XOR the two ciphertext, and the keys disappear, and then we have something non-random, and we don't have problems. So it's called a one-time pad because you can only use it once. And we also have Shannon, who in his Shannon's theorem basically states that, well, if you want perfectly secret, you're going to have a key space which has to be greater than or equal to your message space. And this is a problem, because you need random strings. Those are kind of difficult to procure, and they're really expensive to make, actually. And if you have a large message, you're going to need a large key. So that's a problem. Okay, so we've kind of tried to figure out what else could we do. So we kind of skip the perfect and make it, you know, almost perfect. So we try to relax our secrecy. We have Kekov's principle, and this is a guy who really, it's thanks to him that we even started thinking of other notions of secrecy than the classical, but I'm just bringing it here. And he says, everything about the encryption scheme must be known. Everything, except for the key. The key should be the only secret thing, because you can kind of lock that up and keep it, but everything else could be leaked, and it should still be secure. This is really powerful. But at the same time, he also says, well, let's just make it efficient adversaries, because otherwise they could basically just check all possible keys, and then they could break it anyway. So let's say efficient adversaries. Efficient means polynomial time, which means that whichever algorithm we use to instantiate it is going to be polynomial in many steps. Quantum computers don't have that problem. They're exponential. So polynomial time is what we're talking about here. And we want to say that they succeed with only negligible probability. Negligible probability is a function basically on n, which is 1 over some polynomial on n. That's basically all it means. So whenever I say negligible, just think this. It's very small according to n. Okay, that's basically what I've written there. So, what about private key encryption schemes? This is basically analogous to what we had before, but those were perfectly secret. Here we have like private key. We need to relax some of the things, but it's more or less the same thing. We're still going to need a key generation algorithm, which is random. Again, we're still going to have that k is larger than n, where n is some security parameter. Not going to get into that. The encryption algorithm is still going to take some message and some key, do stuff with it, and then output C. We usually also say that it has to be random or probabilistic, because otherwise we can kind of just compute all possible things. But the decryption algorithm is going to be deterministic. And here you see we also have this error. And that's because we don't suppose that the message space and the ciphertext space have the same length. So we could have some ciphertexts that simply don't decrypt, that don't have any message corresponding to them. But what we do say is that for every message that we may, which we can encrypt obviously, because that's how it's defined, if we were to decrypt it, we get M again. So it's still correctness, it's just not perfect correctness. It doesn't exist for every ciphertext. Okay. Right. So this is the corresponding experiment, and it's the exact same. We have two messages of equal length again, and we basically generate a key, and then this random bit, I forgot, well, I write uniform, so it's random. And ciphertext is computed, same thing, same experiment, and we also say A succeeds and loses in the same cases. Okay? But here is where it differs. The indistinguishable encryptions in the presence of an eavesdropper, or EAV secure, we have a lot of shorthand. Then, if you noticed here, we say that, first of all, now we have polynomial time adversaries, probabilistic polynomial time adversaries. Basically, the polynomial time is to say it's efficient, and the probabilistic is to say that it's allowed to guess. And it might guess correctly on the first try, who knows, but it's a very slight possibility. And what we say is that the success probability is going to be less than a half. Remember, before it was equal to a half, but less than or equal to a half plus negligible probability. So it's slightly worse than before, but not a problematic amount worse. Okay. This is a wall of text. I'm going to explain this wall of text now. This is the greatest tool that we have. One of them, we also have something called hybrid arguments. This is proofs by reduction. This is how we prove things in cryptography, for the most part. And basically it's a contradiction proof. But it relies on something which most mathematicians in here would say is really shaky, and please don't do that, which is we use something which is unproven in order to prove this. Okay, let me try and explain how that works. So I'm going to draw a picture, because that's easier to do, a way to do this. So we start by having some encryption thing. You know, we have a generator, we have encryption, we have decryption, and we want to prove that this is secure. How do we do that? Well, we take a problem X, which is hard, and then we kind of make a reduction. Let me just explain. Hard problem in cryptography means that a lot of people have tried to prove or to solve it, to break it, but they haven't been successful. Then we're like, okay, it's probably not going to be solved, let's just use it. So, you know, prime factorization and such things, but I mean, of course, quantum computers can totally solve that. So, this is also the reason that we really believe that P is not equal to NP, because if it were, there are no hard problems, and then all cryptography falls apart. I'm not going to get into that, but you can ask me later if you want. Okay, so what do? Well, we kind of draw a box. We love diagrams in cryptography, and we say we have some distinguisher D. And D wants to solve X. He wants to do the impossible. Yeah? So let's say that he wants to solve X. Now D has access to something, some oracle, giving him some sort of information. I don't know what, it depends on the problem. But whatever he knows about the problem he can talk to this oracle, which he doesn't necessarily know how that works. He actually never knows how that works. But whenever he sends some element G, he gets some element F back. And he can use that to however he wants. And he has queries to it. But the interesting part is this. Inside of the distinguisher, he has this adversary A, which solves pi. It simply breaks this encryption scheme that we've cooked up with some probability, non-negligible probability epsilon of m. And the whole idea is that delta fakes Alice. delta or D simply acts like it is Alice and kind of simulates an experiment for the adversary, which the adversary then breaks. So D doesn't know how the adversary works at all. He just gets a box. You could say it's an oracle inside of D. But he's able to also send some elements G and get out elements F. Or, yeah. In some kind of regard, they kind of correspond and do that as many times as necessary until the adversary actually solves pi. And then pi, if we run this experiment with 0, 1, then A kind of outputs a B prime and wins the experiment, so I'm just going to write wins with probability n. And then D has some kind of already determined probability of winning. So probability, I'm just going to write. So this is the probability that A succeeds, and then kind of multiply it on some negligible function that says that D is going to solve this, because this is the standard thing. But then this is going to be non-negligible, because we assume this was non-negligible. And now we have that D actually solves X with non-negligible probability. But we assumed that X was hard, and that it couldn't be solved with non-negligible probability. So we got a contradiction, so pi must be secure. And that's basically proof by reduction, and you can make variations on it and really write it out, but this is essentially what it all boils down to. Once you understand this proof method, it's so much fun doing stuff in cryptography. Okay.
So the contradiction arises when we solve a hard problem.
Yes,
Yeah.
exactly.
Okay.
Now,
Yeah.
the problem then comes that, well, what if you actually could solve it? And yeah.
So the contradiction, just to get straight, is the assumption that epsilon of n is non-negligible.
Yes. Yeah. So A solves pi with some non-negligible probability.
And this sort of contradiction proof will give us that the probability is negligible. The probability of success.
Yes.
Oh my goodness.
Yes,
Yeah.
exactly. Yeah.
Okay.
Okay, good. So that's what we use. I'm not going to do it again, but yeah. So brilliant work tool. All right, so I'm getting, I don't know about time. 43, okay. I'm going to try and hurry up a bit because this is basically symmetric cryptography, symmetric key cryptography. And we have different variations. We have this multiple EAV, we have indistinguishable encryptions under chosen plain text, and, you know, different sorts of security, and it gets stronger and stronger. Because if he can do plain text and ciphertext, then the adversary has more to work with. In any case, we also have something called authentication or verification. And before we just had encryption, sure, but how do you know? How does Bob know that he's not talking to Eve? Yeah. So we need to make sure that he's not talking to Eve, and that's what we do through authentication. And these are the MACs, as we're calling them. Might have heard of MAC address and stuff like that in computers. I don't know. But it's basically to say that you're who you say you are. And it works slightly like encryption. You have this key, but then you have this tag generation algorithm. It also basically a ciphertext, but not really. And then we have a verification algorithm instead of a decryption one, which says whether, given a message and given a tag, whether it kind of is correct, whether it really is you. Is it really the correct tag which corresponds to this message? And
So the tag could be a PIN number, for example.
yes, I know it could be, sure. But it's kind of, well, it's a PIN number generated by this exact message.
Okay.
So it pertains only to that message. If I were to change the message, the tag changes. I can't just keep using the tag. The PIN number is a key, essentially. Yeah. So we also have an experiment, this unforgeability experiment, the MacForge. And it basically runs also slightly like the encryption-decryption. And yes, so it succeeds only if it's able to procure a message and a tag such that the verification algorithm is correct, with a message that it hasn't already asked before. Because here's the thing, A has Oracle access to the Mac. If we go back to, so before we basically had that A kind of, the adversary kind of just inputs these two messages, gets some ciphertext back, and then does some work. But here we kind of add an oracle, where he doesn't know how it works, but he knows that he's allowed to send messages M and get tags T back. But then we kind of assume that he hasn't already tested M, that he hasn't already said M to the oracle, because obviously then he's gotten a tag back which satisfies the verification, so he hasn't really broken it, he's just used the back. So we kind of guard against that by saying M is not something he's already asked this oracle. And this working with oracles is a huge part of cryptography, especially in these proofs. And we have, again, some kind of security definition. Here, just negligible, that it basically shouldn't be able to act like you. I don't find this super important or impressive, so I'm just gonna go to the next thing, which is our last thing, nodes and private key cryptography. You can combine encryption and authentication and get authenticated encryption. There's also something called hash functions, where we don't need as large keys and block ciphers. And then there's something that I'd love to talk about, but no time. So, and this is the stuff I work with, pseudo-random functions and stuff. Anyway, yeah. So now we're on to public key cryptography, and this is also called asymmetric cryptography or asymmetric key cryptography, and that's because there are actually two keys produced. And it's sort of like private key, except here, well, we have. Yeah, so here we have two keys, a secret key and a public key. There's a focus on this key exchange thing, and we still use hard problems, but here it's like number theoretic problems that are very good to use, like factoring and RSA. And we have dual notions for pretty much everything. Secrecy in private key is private key encryption, here's public key encryption, but integrity, or this verification, authentication, is message authentication codes, and in public key is digital signature scheme. So whenever you hear about digital signature in the public debate, then you know what they're talking about. Okay, so we have, again, kind of the same definition of everything, but here we then have two keys, the public key and the private key, or secret key. Encryption algorithm follows the same way, but here I'm going to make sure that you notice that there's a random, because it's actually been proven that if it's not randomized, if it's not probabilistic, if it's deterministic, you can easily break it. Always. And that's a problem because for many years, no one actually knew that, even though I kind of thought it was pretty obvious. When you see some of the encryption schemes, then you'll be like, why did they ever do that? But, so there's a lot of stuff on the internet which is actually not secure at all against your usual computer. In any case, here we also have correctness and so on and so forth. Okay, here is something called Diffie-Hellman key exchange. Some of you have probably seen this in elementary number theory, but this is a way, this is not encryption. This is simply a way to get a key to Bob over a authenticated channel, but this is basically so that I don't have to give Bob my secret key. This could be a problem if he's in Canada and I'm here in Denmark. So we only have the internet to work over, which is authenticated, but this procedure basically gives us a key that we can share. I think I'm gonna maybe just skip this. But basically it says that we can do some fancy stuff to get a key across that, so that no one knows the secret key, but or other than ourselves, and Bob also has his own, but we have a common one that we can use together. And again, we have this indistinguishability experiment. Again, it's the exact same, which is nice. You know, we constantly have the same things that we need to check, the same way to prove things. But here, again, there's a difference. And that is that the adversary is given the public key. So eavesdropping indistinguishability actually gives the adversary an encryption oracle. He can encrypt messages because all you have to do is use the public key. This is the entire brilliance behind the system, is that I can give my public key out on the internet. I can just put it anywhere, and someone can then take their message, encrypt it using this public key, and send it to me, and then I'm the only one who can read it. But the adversary also has access to this public key, so he can obviously encrypt anything he wants. The whole point that we get into then in the secrecy is that he can't decrypt it necessarily easily because of hard problems. Right, so again, indistinguishable encryptions in the presence of an eavesdropper, called EAV, and we have the exact same thing. This is again PPT adversaries, and some negligible function has to exist such that success probability is still very close to only half. And yes, so this definition actually gives us CPA security. Like I said, you get this chosen plain text attack security because he has an oracle where he can choose his plain text, encrypt them, and do whatever he pleases. This is an example of an encryption scheme called El-Gamal. And yeah, so here he uses, or El-Gamal uses this randomness in order to make it so that it's not super easy to decrypt it. You need this randomness, and if you look at the proof of security for it, you'll see why. I'm going to skip that though. Other kinds of public key cryptography that exist is something called learning with errors. It's a very linear algebra-based encryption. Not going to get into that either, but it's sort of like you just use vectors and shoot them off, and then you get up to a point where you really want to be, but then you add an error. And now you know what the error is, but no one else does, so whenever they try to do any kind of calculations with it and try to break it, the error just increases, so they get further and further away from the true message. Fully homomorphic encryption is actually pretty cool because it's what Google uses. You can encrypt something, and then you can send it through Google, like they can do whatever you want with it, all the information, without having any idea what the message is, and then send it back to you, and they've done stuff to your message that you wanted them to do. It's kind of weird, but it basically allows you to send secret things, and Google doesn't know anything about it. But they still work for you, it's awesome. Elliptic curve cryptography, if you're into number theory and stuff like that, that'd be definitely a way to go. And then there's quantum cryptography. Now I'm going to differentiate between two types of quantum cryptography. There's the one where you're actually on quantum computers and using quantum mechanics in order to encrypt and show that things can't be broken by other quantum computers. But there's also using classical cryptography and then proving that no matter what kind of computer you are, like quantum or classical, you can't break it. And that's what I'm doing in my thesis. So that's fun. Yeah, so private key versus public key. Public key is very good because it allows key distribution over public but authenticated channels. It also reduces the amount of stored keys because if it were symmetric or private key, then Alice, and I'm going to draw a picture actually of this. So A, B, C, D, E. So if this were a private key, then these two need to share, these two need to share, these two need to share, and they all need to share keys with each other, and then like this as well. There. Right, so you get this, we're summoning the devil when we try to do that. But the brilliance with public key is that it can kind of get rid of everything. Just have this. No. Which is nice, and just meet in the hub, and then everyone also stores like a secret key as well. So we get quite a quite less key material, and that's a very good thing. But it's not as good as using private key because it's a lot slower. Because you have to make sure that no one can break it and stuff, and you have these two keys. So there are more operations involved. So if you can, then use private key. Yes, that's pretty much it. If you have any questions, yeah.
So at the beginning you stated perfect correctness,
Yes.
which is sort of that encryption, decryption, given K are bijection with
Yes.
each other as an inverse.
Yeah.
Then you define correctness where they cancel from the right but not necessarily from the left because encryption might not be defined on.
No, encryption is defined on
On
all
all N.
messages, but decryption
is not defined on all C.
Yes.
Why would you add, but isn't the second form of correctness always better than perfect correctness?
Yes.
Because you have some, so to speak, some red herrings.
Yeah, exactly. You have noise or so. Yes, but in perfect correctness, you need it. Otherwise, you don't have this 50-50 chance. Yeah.
So you stated that almost all of the problems that quantum computers could easily solve them. What is it that quantum computers?
I didn't quite say that. I
Okay,
said
sorry.
some of them, like
Okay.
RSA, can be broken,
Okay.
but there are still quite a few that we don't know.
Okay. So what is it? Okay, so quantum computers can exceed polynomial time, and how do you sort of guard against something which can utilize exponential time?
You limit the amount of Oracle queries that it can have. So,
Okay.
because, so this is, again, the quantum versus the classical. So if I'm in a classical setting and I want to guard against quantum computers, I make sure that their Oracle access is only in a classical sense, like they have to send bits or bit strings or group elements or whatever to the Oracle, who then does all the work and then sends it back. In the quantum case, if it can have a quantum oracle, which means that it can query things in superposition, and then magic happens, and it can actually query a lot instead of just polynomially many things. So I basically, for example, in my thesis, I take the classical case, then I say you're only allowed to talk to the oracle in purely classical sense, and you're only allowed to ask Q things.
And when you say Q things,
Polynomial.
You said something like that public key would only be secret if you had a probabilistic algorithm.
Yes.
But isn't RSA secret in the sense that factoring numbers is a hard problem?
Yes, but in the actual encryption algorithm, you throw in some randomness.
In RSA?
Yes, you should be doing that. I can't be sure right now, but it's an actual theorem that says it has to be probabilistic, the encryption scheme. So I'll look at RSA and then try to point something out. Yeah.
So this oracle thing is still very, very mysterious to me.
Okay.
Could you maybe elaborate maybe some sort of, I know, mathematicians hate stuff like that, but could you maybe give some sort of real life analog or something?
Yeah, sure. Okay.
Right now it's sort of like some person.
Okay, here it is. So the NSA really loves to mess around with our computers. So what they do is they get the ciphertext that Alice had, and they have access to her computer because they put in an actual device which allowed them access to it. Like they can just go straight through her firewalls and security Windows logon. But she came from an outside source and put in like her key, her random key. So they don't know her random key, but she put it into a program which is on her computer and then locked it in some way. Okay. So now the NSA, they can't see what the key is. That's secure in this program, but they can use the program because they can log onto her computer and then write some message and then ask it to encrypt it. So now they have an oracle. They don't know Well, okay, let's also say that the program is completely like locked. Like they can't access the program because the people who made that were very clever and kind of put it in a titanium box somehow or something, right? So they can kind of use the program, but they don't know anything about the program.
Okay.
And that's other than what it needs as inputs and outputs.
Okay, so it's sort of like an end user who doesn't know anything about a program, just how to use it.
Yeah, basically.
Okay.
Exactly. And we like to call it black box scenario as well. Yeah.
Could you maybe say a few words about this elliptic curve cryptography?
No. I don't know anything about it, but there will be a course here in the next block called Elliptic Curves with Fabian Pasuki, and he has promised that there will be a part of it at the end, like last week maybe, where they also talk about elliptic curve cryptography. But I think it's also in the Intel book. Just a little bit about it. But anything else? Then I'd like to say thank you very much.
Elsa Krasner, public key cryptography